Yes, let's start. So let's assume that I work for a company. I mean, I work for a company, but let's assume I work for a kind of an imaginary company. And there is this business analyst, and he has a nice idea. He said, let's not make a doorbell system. So his idea is you have some small microcontroller board. It's connected to some push button. Then there is some speaker. You can press the button, and the doorbell will ring. So now that's not that fancy at all. And I mean, even why would you need a microcontroller to just ring the doorbell? But his idea is that you can connect it to some internet module. So that can then communicate with the internet. It can post to Flickr or whatever, Twitter, what's going to happen at your doorbell. You can also configure your device with different doorbell melodies via a web interface. So let's go and implement that. So let's assume my company with my team, we had the first sprint or iteration. We have kind of the first customer presentation. It will take place in about 15 minutes or half an hour. The customer is on its way to arrive. So let's see, you get like a preview of the customer review or presentation. Maybe I'll show that back. All this stuff it's here on the table, so if you have a seat in the front, you see really the stuff. The back, maybe you don't see that much. So, okay, let's ring the doorbell. Maybe here, this is kind of Tomo-kun. There is another like this rabbit. It's kind of the visitors. He's going to visit, presses the doorbell, maybe be silent. You hear the doorbell? Now let's see what happened. Okay, there it is. We have a picture of the visitor who rang the doorbell. Did I say the customer is on its way? There's something wrong there. It's upside down. What are we going to do? What do you normally do if you're late in project? You should deliver, you're not ready yet. Yes, that would be kind of intriguing, but he knows how it's going to be built into the physical stuff. Any other ideas? What you should not do is hire more people. But that's exactly what we're going to do. So I want to hire somebody. Some volunteers, somebody sees that matches his profile. Maybe because we're in a hurry, it's maybe the assessment is not that difficult. Maybe you can sleep even if you don't really fit the profile. Any volunteer? Come on. Okay, yes, please. You're now the new employee. What's your name? Just need to set up to do some IT stuff. How do you write your name? I-N-A? Yeah. Very nice. Okay. Yeah, you can take place here. Yeah, you're going really to do some work. And this is kind of what you should type or do. You're familiar a little bit with? Yeah, starting from here. I mean, that's kind of the command. And if you want, you can tick off that you don't get lost where you are. I will comment what she's now going to work on a bit.
I need to set my password to this.
Ah, okay, yeah. Let me make this confusing. Yes, the password. Her very secret password. Please don't share. So now she's really, I think I did a really good assessment. She's half a minute into the job, she already starts to check out, clone the repository. I mean, you can stand in the middle, but then I'm in front of the screen. Wow, it worked. That's nice. I was not sure if the network connection is. It's not possible to turn it down. Okay, now she started already to build the software. Quite nice. And there is also tab completion if you don't have always to type all the. You can, if you writing make and then start typing, can use tab to.
Okay.
Yeah.
Do we need to wait for it to finish?
Yes, yes. Yeah, it takes a while. Just one question. Who was able to start his work, get his PC, and I don't know, maybe it took 5 minutes until now to already start the build? Maybe who is an embedded software engineer or working in embedded? Oh, not that many. How long does it normally take to do your first build when you start in a new? I mean, yeah, depends if you start a new project, then you first need to get all the toolchain, but if you come into a project that's already running. Some numbers?
2 days.
2 days.
Want to download all the correct images and install them again, the third time, and then fetch the different drivers for Bluetooth, for whatever, which actually communicates with your device.
Now what she did, she executed some tests, and as you can see, there was a failing test. Somebody already saw, okay, the picture should not be upside down. There was already a test, very nice. So she already somebody did some work before. She's typing here, the screen.
Security reasons, right?
Should I move it?
No, it's okay. Or maybe I don't know if we could make the window.
That is better.
Yeah. Like that. You can also resize the window if you want. Yeah. Yes, you need to edit in the window. Maybe you can also double click on not just there in the.
I'll use that.
Or you can double click here in there, and then it will just be full screen, yeah, like that. She already got into some code. That's something maybe because we're discussing, you missed it. She also executed unit tests, and there was some disabled test. She's now got to the place where there is this disabled test. Yes, just delete and save and close it. Now she's executing the tests again because she took back that disabled test. We see there is a failing test, picture shall not be upside down. So that gives us a hint there is something not ready yet. Yeah, just somewhere in that.
Oh, I don't see it.
Oh.
I was still thinking I could have turned the device in a matter of seconds.
Yes, of course.
None of it's already built. None of all the tooling is sorted out. It's like, he's probably got 1,000 of them already built. Yeah?
Yeah, sometimes that happens, it would be a very easy kind of physical or hardware engineering.
It's never that easy.
But normally it's already ordered or some boards are already produced and you just have to solve it in software. It was still failing.
Look at the code again.
Ah.
You put the minus
Can you-
the flip. You put the flip in the output.
Sorry?
There's minus O specify the output file. And you put minus HP minus.
I don't
Ah.
know. You try again?
Yeah, it just opened the editor. Maybe. You can also
Oh,
you have
sorry,
you have the history here and can.
Do you need that one?
Ah, yes. Yeah, that's nice. So you need to, yeah.
We should have seen it.
That was not intended, but a bit intended.
It's a good example.
Because it's a very good example to see kind of make some silly mistake and then we had the feedback, what happened. Yeah, just execute. Hope it's saved. Yeah, green. Now she's executing some acceptance test. There, now it looks a bit suspicious what we, I mean, there it said it's failed, but here you see it's green and it said it was not, I didn't expect it to pass. I will explain this later on what happened, but it's now, the scenario passed, so the picture is not upside down now. Oh, just type yes. And you didn't need to type yes if you're really sure. Yeah, and now you can start, I think it's, yeah, you can do the demo if you want. It's here. Reload. Thank you very much. Some applause for.
You're going to send her a check, right?
Very great. Yeah, I will hire her immediately. Very great job. 15 minutes. She implemented one feature. I've never seen that. Okay. Now maybe that was a little bit fast what was happening because she went through a whole development cycle in 15 minutes. Now let's rewind a little bit and look at things from start. So my name is Raphael Meyer. I work for a mid-sized contracting consulting company based in Switzerland. And normally, or almost always, I'm contracted as an embedded software engineer to customers. Normally I work at the customer side. It's very seldom that embedded projects get really outsourced to the contractors because it often involves hardware and then you would need to get the hardware there. There are a few problems. When I arrive at the project, that's maybe the nature a little bit if you're a contractor, they don't call you if everything is smooth. I see like that situation. Now there's really a lot wrong in this picture, but I will focus on these three guys here, not on the rest. I mean, I hope you enjoyed some other talks which speak more what's wrong with that in the upper corner there, or there. And one of the problems is, I mean, the salaries in Switzerland are very high. Now that doesn't sound like a problem. Everybody likes to have a high salary. But companies, especially international companies that kind of are based or not based, they just have, for historical reasons, have still some development centers in Switzerland. From the company perspective, it often looks like what you get out from Switzerland and from somewhere else. The only difference is maybe this price tag here. Normally it doesn't even say Swiss made. So if you have that, you have more or less two choices. Either you can sell that brand very well and say, just because you like my brand, it's more expensive, or you really, here it looks very similar, it's kind of the same, or you can really show off that there is something better, that you really pay more. Now, from the projects I see, it looks some kind of pessimistic, because from company perspective, what the developers, what the developers deliver doesn't, from the company point of view, not really look that much better that you would say it's worth to get it done in a place where the costs are much more higher than everywhere else. But I still think at the moment we can still produce products at competitive prices in Switzerland, but we really need to kind of get done. I also see a lot of place to improve at the level of the developers or the development. I still have kind of feeling they're stuck somewhere in the 70s or 80s. I also often get to companies where there are really people that they are 10 or 5 years before their retirement, and they work their whole life in the same company. So they have maybe 40 years of experience on the same stuff. They always did it like that. And so one of the things I see that really people need to catch up in this environment is to apply engineering practices. So let's have a look a little bit at that. I hope I don't need to tell anybody in this room that you need a version control system to store your source code. But I still, in the environment I get to sometimes, I never got into a project where they didn't have version control system, but what you often see kind of, yeah, they're really behind, lagging kind of 10 or 20 years behind. If you don't know, just Google for GitHub, make an account there and try to find out what it's all about. I think it's a good start. I won't explain more. The second thing, if you get our source code into the version control system, what we want to do then is kind of that there is a continuous integration system that will take that source code and do something with that. I don't know. I hope also I don't need to explain what the continuous integration system is, or somebody not familiar? Not, I hope. But that I really seen that the companies, sometimes they still don't know it, or they know what a build server is. They don't really know it. They just know build server is something you do nowadays. So you need one. I also recently got into a project where they had a build server in place, but they didn't know what it's good for. So it was just there. It sometimes compiled some source code, but there was no feedback out of it. So it's basically, you could put there just some box there, cardboard box, it's the same. Some of the reason why this happens is maybe also that people, they confuse that kind of continuous integration itself is not a machine like a build server. It's continuous integration, says we integrate something. It's about the process. And the build server is kind of a tool to help you with that process of continuous integration. And the continuous integration is about getting then the feedback back. That would be the feedback we want to get out of our continuous integration system for the developer. And as kind of a second nice thing, you also can get out automated builds of your software, your images for your devices or wherever. You get the artifacts that you can deploy on your device. Yeah. That's the device. Yeah, maybe if you see something like that, that always means a device. The important part about continuous integration is that that's the place where you automate your stuff, that it should show kind of the health of your, it's like of your project, it's a little bit like the monitors in some intensive care station. And it should be a little bit like a cockpit in an airplane, used as a metaphor. So you should see all the important stuff you want to see or the feedback you want to get from your continuous integration system in one place, that you don't have to go and look in other places. That's also something I saw some customers, they had the feedback there, but it was really distributed. And because you need really to look it up yourselves, the developers, they stop looking at it because they're too lazy for that. Okay, what we've now seen is we have source code that gets into the version control system. It gets built with feedback on the machine, and that's the problem. How do we get our source code built? Either on the continuous integration system or at the development station. Now with embedded system, building is often not so trivial tasks. You often, when you start at a new place, you get this famous Word document called How to Get Started or Cookbook or whatever. It's the typical 2 days. You read through it, you install stuff on your PC. Maybe you still need to maintain the previous project. You will not be able to build it anymore, or you cannot build a new project because you only have like 2 versions of the same tool that are not compatible with each other. You know this stuff. That's normally what you get. Also, the tool chains are one problem is they're not so simple. Sometimes you have a compiler from one vendor, you have an operating system from a vendor, you maybe even have an IDE that needs to kind of operate with the compiler and with the operating system that you can build your stuff. I mean, even you have it also if you do C# on Windows, it's not that different that you have kind of, you need the runtime for the .NET, you have like dependencies to the operating system, but there it's just, you use Visual Studio and it's already kind of configured because it's homogeneous. You're not going to develop Windows C# applications on some other machine. But In embedded, often these components are from different vendors and they somehow need to match together. So one thing I tried out is why not try to use all these fancy containerization or virtualization features and try out to build up a toolchain based on that. So Docker is now quite something that developers seems to like. For toolchain integration, you need to consider a bit what you really want to do if you want to virtualize your environment, your development environment. Maybe Vagrant, which is kind of a layer to automate a virtual machine, really, where you can have with a graphical user interface and whatever, which really provides a full virtual machine, is maybe a better option than Docker, which is really kind of on the low level and really small, or maybe something like Linux containers. So you need a little bit to figure out what really fits your need. Maybe also you need, one is maybe for the developer machine, one for the better suited for the continuous integration. What I did a prototype with Docker. I don't know, who does not know how Docker works, basically? Oh, okay. Then I will explain short. Docker introduction in 5 minutes. In Docker, you have base images which are already prepared for Docker. That's normally something often you don't do. That a few guys take this work. I think it's so complicated to make a base image for Docker. Maybe for if you don't know Docker at all. So Docker is a very thin virtualization layer which is on top more or less of the Linux kernel. And if you compare it to a virtual machine, with a virtual machine you really boot the whole operating system. And with Docker you kind of you use already your host operating system to execute stuff inside your container. They're very lightweight. Let's go back. We have this image. Then we have a Docker file describing what do you want in this image additionally to what's already there. From that we can build another image, and then you can go on and go on. That's kind of the interesting part, is that Docker is built in a way that you really profit from that. If you have two images that have the same base, you only need the base once. I mean, you need the base once. If you want to get these two images, they only get the common parts. They get only once, which is the base. Now, what you can do with that image is you can start a container. The container is like this running environment. You can execute commands in it. You can multiple times execute commands. What you often do with Docker is you only execute the command once, and then you already destroy your container. They're so lightweight, so instead of a virtual machine, you would boot it up and use it for some time, and then maybe end of the day shut it down. And with the container, you can you use it often just for one command, and then destroy it. Then start the next and destroy it. If you now have these containers that execute stuff and you always destroy them, you want to store your data somewhere, which is in the container. And one way to do this in Docker is to have an extra container, which is also a Docker container, but it will never be run. There will never be a command to execute it in there, but you just use it to map a file system. You have a volume which is associated with the container, and you store there the data and link together these containers to kind of get the data there. Now a small example with the one that was in the doorbell system, the small microcontroller board. It's an Arduino board with it has some 8-bit microcontroller in there. It's called the architecture is called AVR, and there is this AVR GCC that's in one container, and which executes. There is also CMake in there. It's all the stuff to build binaries for that, and then we have as a build workspace just this data container where everything gets stored, what's to be stored when we're building, and out of there we can copy out the binaries. So let's see how this looks like. I want to show you then a second window. Yeah. Okay. Just clean out all the build artifacts. See, there is nothing in there. Now, what I start here is, it will show you what containers are there. Now at the moment there is no container, so it's just the titles there. Now I built my executable for my Arduino binary. Now you've seen there is this AVR workspace is popping up. It's already built. So did someone look close? It's maybe, now it's even faster than before, because now it doesn't have to build again. There is a second container popping up. That's the container that builds. And this one is this data container that holds the data, or the build workspace. And now if I look back, we have two binaries there, or binaries. Get rid of the noise. Oh, I'm still. I was still building on her in her account. Because now there is I will just show it and then clean up after. There are a lot more files in here. If we look at the one that was built was this hex file. That's, for those who know, that's and the other one, which is built first, in fact, and the hex file is extracted from there, is a ELF binary for this AVR 8-bit. Yeah. Then the more interesting case is for there is a Raspberry Pi, for those who don't recognize it, it's a Raspberry Pi. There I use the Yocto Linux. Yocto is, it's not the Linux, it's a build system to build your own Linux distribution, which is very popular in embedded projects. And there it's a little bit more interesting, because first of all I need to build my Linux. That I do with a container again, which contains all the tools I need to build the Yocto Linux. I have a workspace where all the binaries are placed to build it. then out of this workspace I can copy an SDK. So when I build the Yocto Linux, I not only generate my operating system image that I can deploy to the Raspberry Pi, I also get an SDK. Yes, and the OS image, which I can just put on for the Raspberry Pi, just goes on the flash card. And the SDK, this provides the compiler and the root FS and all the stuff I need to compile a binary that runs now in this Linux image I have built. And this SDK I install into another container or create out of it a new container. Then I have a new container which contains the SDK installed. So I have a container with which I can generate binaries for the Raspberry Pi. Yeah, and there I also use a data container to build it and get out the application which I can deploy to the target. Now the interesting stuff with Docker is that they have, you normally put your images into a repository and they are tagged or versioned. So you can put the tag on it, and often if you have bigger teams, not every developer will be messing around with the Linux. You normally, if you have maybe 10 people, you have 1 or 2 persons or maybe 3 who are the experts on the Linux side, and they will mess around, or not mess around, but sometimes it is a bit, but get your Linux working, and the rest of the team, they're focusing on developing the application. So now the persons who work on the operating system, they can work on, and when they think we have something we can release, they can tag their container. You can also automate the whole stuff in your version control system, that you tag your source files for the Linux, and then you say, yeah, get me a Docker image out of it, and then, because this will build very long. It takes about, on my high-end machine, for the Raspberry Pi, it took me about 2 or 3 hours to build, and I have a small old machine that I use as a build server, and there it takes over a day, 26 hours. Yes?
Excuse me, I don't quite understand. You're saying you build your a Docker container, which is the environment that's going to be your embedded environment, and then you build your embedded product in that container. Is that what you're saying?
It's you have one container which has the tools just to build the embedded Linux for the device.
Because another way I've seen it done is you build everything on Linux rather than the type of device, but you build it with cross-compiler.
The cross-compiler is what ends in here. No, it's not only here. If I call this container here, which is for building my operating system image, the Yocto is something, what you need is a GCC and Python and make more or less, maybe a few more tools. And it will create a cross-compiler which you configured for your target, and will compile everything that it needs to build the operating system with the cross-compiler, and the cross-compiler ends up in this SDK. Which the SDK is then just, you can also just use what ended up here in this workspace to compile the applications. But because the normal application developers who are not interested in adding new operating system features, like adding libraries or configuring something, they are happy with just the SDK, which is enough to kind of just only compile the application. Did I clarify your questions, or you could maybe compare it with, like, here you build the JVM from source. Here that's the SDK or the JDK. So the Java developer just wants the JDK, which would end up in this container. And in this container you build the JDK from source. Would be kind of the analogy. Yeah. And what I said, the interesting part is that you can you can version it. So we have control over it. So if I version my containers there, and also put my OS image somewhere where I can store it with a version, then I know if I have OS version whatever, it will match exactly with the toolchain I have in container version 2.0. Yeah.
Yeah, you can also, have different containers that contain different tool sets.
Yes.
So if you decide to try a new compiler, you don't have to install it over your existing one.
Yes.
And they won't ever conflict.
Yeah. I mean, that was the main motivation that, I mean, you see before I had to use a GCC for that target and then another GCC for that target, or maybe I want to use Clang for that target. Yeah, let's look on how this looks like. Oh, I didn't clean up yet. So, okay, I cleaned it up again. Now you see I've cleaned up all the containers. So what I've not yet set up is that it's kind of multi-user aware. So we share the same workspaces, therefore I have to clean up. So you see now I have this YB Pi workspace. That's the kind I gave it this name for the toolchain for the Yocto Raspberry Pi. So there's a Y for Yocto and the Pi for the Raspberry Pi. And the artifacts now contain my application I built. You can see it's a 32-bit ARM binary. Any questions so far? Now we kind of have our tool chain in place where we can build for the target. Now what we want to know is what do we really want to build? That's something, it's not a problem of embedded software engineering or not, but unfortunately I don't know if they're not aware of what kind of methods would be there or what discussions are going on in the whole community, or if they're immune, or if they're not listening. But I often see that they really struggle. That's one of the main problems they have, that they don't know how to find out what they should do. In my opinion, I mean, you need to involve the people who give the money, or the ones that somebody is going to pay and he wants something for your money, and you need to involve these people and kind of get the process where you really find out what. I won't speak about that, I'm not really an expert in that. I mean, there were a lot of experts here at the conference. I hope you enjoyed some of them. And some starting points that I find interesting is kind of getting involved with PDD. And some book that I read that I think it's quite new from Ron Jeffries, which is, it gives a new perspective on, he tries to explain Scrum or Agile without using these words because they're kind of overused and often associated with misbeliefs or kind of with wrong belief or wrong understanding. Oh, you want? Another, what's also important is kind of that to find out what with this discussion between business people and developers and everybody who's involved in between, that the feedback from your software is important, that you can kind of, we can close that feedback circle, because in the beginning nobody knows what you really want. You need to find out, and feedback is a good way to find it out. And that's also something, I don't know if it's particular to embedded software or not, that you need to learn how to communicate this feedback, or how to do it, that you really get good feedback, and that it's not going to, can also backfire if you communicate the feedback in the wrong way. Often if you don't do a proper job and then you communicate what they want to hear and not what you really should have or where you are. One way to make sure that when you show the feedback that you are confident that this is the right thing that you did, is acceptance tests. So we want to get out of the what, we want to get acceptance tests. And the acceptance test should be, a good acceptance test is something that should define when a feature is done. That's kind of the most important stuff, that you, as a developer, you cannot slip, you cannot show like the happy path, and then you do this for feature, and then you look very fast, and in the end, when you want to release, because all features have been seen, they're working, you say, yeah, now we have done 10%, and now we need to do the error handling, which is the other 90%. This good acceptance test, they should really say when you're done. Acceptance test should also be kind of something that all the people involved, all the persons involved, that they understand what everybody means, that there is not so much misunderstanding. And they should be automated as part of the continuous integration system. Now, who writes this acceptance test, or how do they get in place? Of course, it's important to involve the business people, because they know what it should do, but they're normally already satisfied with the happy path. When they see, yeah, the feature, you press there and the doorbell rings, then they're fine. And then you should also involve the testers or QA people who have a different perspective. They're going to ask, if I press the button 2 times very fast, what's happening? Or if I will keep pushing, or what's happening then? And if I put out some cable, what's then, and whatever. So they come up with these questions. Now, to show example of acceptance tests. Yes, it will take some time, because I need to compile the library I use there. Somebody knows Cucumber? Few. I choose here as an example, I choose the Cucumber framework for acceptance tests. For kind of one reason that I find very interesting is that normally your acceptance test is something bigger, and if you want to write it first, which I think you should do if it's feasible, to write the test first, because it gives you an insight on how to further develop on. If you write the test first, then you have a test that of course does not pass, because there is no implementation there. And Cucumber has a nice feature that I can say, I want to execute my work in progress. There was this WIP, work in progress flags. And in that case, I can execute the test Also on the continuous integration system, no, that what do. But I can execute the test, and this cucumber framework will tell me, okay, your test failed, but because you used the work in progress switch, I was expecting the failure. So this helps me that I can check in the test. It won't disturb the other developers because I checked in a failing test, but everybody can kind of execute it, and it's already in the version control system. I can share it. That's one of the nice features that I think should be somehow there for acceptance tests. If you use some other testing framework, for example, I often use Google Mock or Google Test. There I sometimes use kind of the trick that what we've seen before when Ina was doing her work, that there was a disabled test. That's kind of a trick I sometimes use to already get the test there, that I can check it in, share it, but then disabling it that it does not interfere with the other stuff. The tests themselves, as you maybe have seen, there was this nice text there. The test here, that Cucumber is a tool that is from the BDD community. But I mean, just using the tool doesn't mean you're doing BDD. BDD is not about the tool. But I still, even if you're doing plain acceptance tests, it's nice to use that, I think. Or it's one possibility of framework. Yeah, you can see there is these textual descriptions, and all these statements with when, and, then, they will map to some code, which is then, you can separate kind of what you want from your test to describe your system from then the test implementation, where you need to kind of, you can hide a little bit, or you have two levels of abstraction. And what I also could show you is if I mess around with the VIP. Now I mark the test work in progress, which is not really work in progress. And if I execute again my work in progress, that's what we've seen with Ina before. Now I implemented the whole feature, and then we have this upper test which is passing, and then it will tell me the work in progress was used, but it did pass, so there's something wrong because the work in progress should not yet pass. Then you know you're done, you can remove the work in progress and move on to the next feature. When you have your acceptance test, this should give you the input to test drive your implementation. I think TDD is something that often embedded engineers say they can't do TDD because it's embedded and hardware and it doesn't work. But that's why I built this kind of whole prototype, or to show that how you can kind of do these practices. And from the TDD cycle you will get your source code, which then we have more or less the loop closed.
Can I ask a question?
Yes?
I agree with the part that you can do test-driven development the very same way, but I really was the previous context that how your test actually runs, because in order to execute those scenarios, you should push that button. It said a
Yes.
scenario that when I ring
Yeah.
the doorbell,
Yes.
that it means that it takes the picture, and you take that test paused without.
Can I come to that later on?
Oh.
I will ask you again at the end if now answered the question. One problem with TDDs that I've seen is that it's very hard. You really need to exercise and practice it. It's not, even if you're a good programmer, it's something very different, or you work different. It's like if you're maybe a classical pianist and you want to play jazz, you cannot for the first time just go in there and say, I'm a pianist, I can play jazz. Maybe you need to exercise it, and you need to exercise also a lot to get good at it. But often developers, they think kind of, I know how to program, it's a piece of cake. And it often gives the situation if you want to start teaching somebody TDD that they very quickly they get bored because they think all this, like these boring exercises are very boring. Even if you see that kind of they really struggle with TDD, even with some simple exercise, you see they're struggling, you see what they're doing, but it's hard to explain them kind of that this is not yet TDD, you still need to exercise. So what I'm now executing here I will go a little bit more into your question. These are just the tests I execute these are the tests that were built during the TDD process to test drive the implementation. And these tests, I don't want really to have them on the target to test drive it. I want fast feedback that I can just say make, and it should just compile what's new and execute the test. I forgot the S. And then just get the feedback from the test and see if it worked. And then I also have tests for the Raspberry Pi, which also are not yet now on the Raspberry Pi. They're also the tests that were grown during the TDD cycles, just implementing the application there. And for that this works, now it's okay. This would be an example of a test that was used, or tests that were used to test drive the implementation. And you can, there is a little bit of context there. Some of the stuff look like real implementation. It would be really something that I also it's not instantiating. This is C. The tests are written in C++, but the implementation is C. That's something that's really used on the target, but here we see there is a SPI for the PVM. So I use a SPI there, and in the test I then have something that I press the button, that's kind of a helper of the test. Let's simulate that the button was pressed, and then just inspecting this SPI is really, was the bell turned on or off. But I can also go further down, and for example, here I call something that normally, if I install the correct interrupts, that I have my interrupt routine that would be called, and I can just kind of do this in the test. And then there is, that's up there. You can also see that there are some magic variables. I didn't name them myself. These are the registers, the I/O map registers, and on the target you would really get one. And here for my test environment that I run on my host compiler, I just kind of put there the variables that kind of simulate what you would then have on the target. I mean, on the target normally for the AVR, I think it's a nasty macro that then ends up with a reference or a dereferenced pointer, or another S itself, I don't remember. You see, then you include this from the toolchain for this device. You include the header file, and you get them. And in the test, I don't include really the device header files. I have like a test stop of that. Yeah, just to get a little bit in touch with TDD itself, I found this a very excellent book. It's one of the best books about TDD, and it's even for C++. I must say, I think he's not really a C++ programmer. I don't like how he programs, but how he introduces TDD I find is really great. And the whole cycle with the acceptance tests and that drive the TDD cycles, there is a very excellent book by Steve Freeman and Ned Price. I think both of them were at the conference. At least I've seen Steve. This is a Java book, but I think it should be very also readable for C++ programmers. And what's interesting there also, they show that you don't need a special framework for acceptance tests. I don't remember, but I think they just use JUnit. And also the acceptance test, the high-level test, they just use JUnit. And they show some tricks if you just also want to use Google Test for acceptance test. How can you kind of write your tests that they show a different level of abstraction on the test, that you have like this kind of readable form. Now I've talked about the unit tests and the acceptance tests, or the tests that come from TDD, but there is a lot of more about testing. I mean, you can also have tests in between. I will also show after a little bit what is then special to embedded. But what's important here is normally you have there is this testing pyramid, that tests that are hard to execute, that cost a lot, that are hard to maintain, that they are on the top, and the easy ones that can execute fast, don't cost that much, on the bottom. And what you should take care is really that if you order your tests in that way, that you get the pyramid and not the cone. If you have that, you have a problem, because then you don't have much of fast tests that you could execute always, but the tests where the feedback is very slow, you have a lot of them, and then you have a very slow feedback cycles. Then some disclaimer that sometimes TDD is not really that appropriate. Before I showed this, you've seen these registers that were in the test, so the test really goes to the hardware boundary. And now for a GPIO, this device, it works quite fine to do TDD on that level. If you're maybe implementing a USB driver on an ARM, there you have a set of about 10, 20 or 30 registers that you have to care about. Then maybe it works, maybe not. I still have not really kind of the experience to tell how far you should go and really make sense or not. Sometimes really you have the stuff that you can do it, but it doesn't always mean that it's really the appropriate thing to do. A second something which is also special, a little bit about embedded, is you have to find out where to cut, what I said before, where to cut your testing boundaries. Should you have a test double for the GPIO? Should you go until the IO mapped registers? And one strategy to find it out a little bit for me is, especially if you start with acceptance test first, then you still have, especially in the beginning, if you start with a new system, you have not that much knowledge on what you want to do or where it's going to go, or even how your hardware works, is to kind of set my boundary quite on a high level. So maybe just have it on some higher level software components. And so to abstract more or less all hardware stuff with test doubles. Then I go into the TDD cycle. And there I get more knowledge about the details. And then I see maybe I can push my test boundary a little bit further. I can go near to the hardware. And if I found out that I can go further there, I can get that feedback back to the acceptance test, if it makes sense. It's also, sometimes it's a good idea, sometimes maybe you say, no, I already quite confident from my TDD cycle that this is working. I leave it here on a higher abstraction level in the acceptance test because it would kind of make my acceptance test a real mess, because there are more components involved. That's kind of the aspect, especially on the tests you use to test drive. Some tricks on how to get near to the hardware with your tests is the book from James Grenning. Somebody will maybe know him. He was here like 3 years ago or so, 2 years ago. You made a workshop. Yeah, it gives you some inputs on how to do this. The book is also, it's focused on C, so there is also a lot of other stuff. It's not only about TDD, he also explains some stuff on how you can write your C code, that it's more C++-like without C++, but you organize your code. To have one example of what kind of tests are there from the TDD cycle running on the host system. So each of these color-dotted box is like one test context. And you can see, for example, we test the GPIO on itself, but we have kind of, this would be the hardware here, the IO mapped registers. And we have test doubles for these IO mapped registers. So we test until kind of really the boundary between addresses in the memory and the hardware. And for something else, like, for example, the device, we have, we use a test double through some kind of C interface for the PVM, but the PVM itself, there is another test, but we don't, in the device test, we want to kind of get it here. We say, no, it's too much fuzzling, we will kind of draw the test boundary here at that level. That's some stuff that's, I think that's something that's really particular to embedded and maybe a little bit harder. You need to kind of get exercise what it's appropriate and what not, compared to kind of traditional or not embedded software engineering. Yeah, I showed you already before a little bit this register. I will move on a bit and then show off a bit more. Now it's more to your questions. I now always spoke about tests that were running on the target system. But it's important to at least run it also on really on the target. Because in the end, that's something that that's maybe a little bit dangerous. It really speeds up the development if you really get into development cycles with fast feedback on the host system, but in the end it needs to run on the target as well. So you need some kind of a
Just for clarification, what you said that the previous tests which we saw running were actually running in an emulator environment and they didn't do anything.
Yes, yeah. But we really need to have tests on the target. These tests are normally, they're not really quite feasible for test driving because the feedback is maybe too slow. But, and also it depends a bit on what kind of system you have. If you have a Linux, it can do quite a lot. On the 8-bitter, you could do unit tests on that one, but you need to first find a test environment or framework that fits there. I mean, the easiest one is just use the assert.
Test environment?
Yeah, test environment. I mean, the easiest one you can use as kind of a fallback is just assert. You write basically your own, you don't have test framework, you write with test with assert.
I had a test environment on devices that meant this much code.
Yeah.
Then the monitor which accepted the letter A as executed some test, the letter B executed some other test. So I didn't call it environment. So
I mean testing environment, And then, and also if you can, you also should try to automate that in the continuous integration system. Because if you have a good cycle where you can develop, like separated from the hardware, there is also the danger that you're going to break something only on the target, and if you don't have the automated tests, your continuous integration system, it's easy to miss them. And then they only come up when somebody by accident, or not by accident, but maybe after 2 weeks, let's look a little bit at the hardware, and then you discover it has been broken for 2 weeks. And for that, you kind of would also need to get your test feedback out of the device. Therefore, so real kind of unit test level is often harder with smaller devices because it's hard to get the feedback out of the device. Then there, so often you do more like acceptance tests that test the device from the outside. But it also really depends a lot on what your device is doing. I will maybe show a few examples. So for test driving, that's what we've seen so far. You can test on the host system with test doubles. Then maybe you can just use your tests that you also have on the host and just compile them for the target. So with the framework I used, I won't be able to compile it for the small one, but for the Raspberry Pi, I will be able to compile the unit tests for it. This is one thing is it's a good compatibility check if kind of your code is fine with the target hardware, but if sometimes there are some differences, but the tests won't reveal that much. Maybe if you have different architecture, maybe your building system is 64-bit and the target is 32, you maybe find some little stuff where you have kind of dependencies of. But normally you don't really find a lot because it's test doubles. What you can also try to do, that's an example for that, is you could make special unit tests for your target, where you kind of try to interact with the hardware. Now, if you have some hardware device, for example, like an EEPROM or a RTC, you can really write a unit test that maybe communicates with it and you're not depending on input from the outside. But if you have, for example, a GPIO, you need to add something that you can interact with that. For GPIOs, you could, for example, have a loopback, but then you're not on your real product. You maybe need to have a modified hardware of your product, or you have an evaluation board of your hardware where you can run this kind of tests. And for other stuff, it's then maybe even harder if you have a temperature sensor, or how do you simulate temperature? I mean, you could do it, but is it really a good idea to do it or not?
If you have 3 minutes for an example,
Yeah.
so on one device I had to program a flash memory. The flash memory really is now quite sophisticated. It has some 7 commands for basic operations like read a block, write a block, flash a block, stuff like that. And that can be really tested anywhere but the hardware. But it has plenty of attached functionality like error correction logic, bad block handling, and stuff like that, which is quite opposite. You can't realistically try it on the chip because it will not generate you bit errors where you want it and plenty of other stuff. So I had to create a full emulator for that chip by the specification, which did exactly that, but allowed me to inject bit errors and all kinds of bad stuff, and that was tested completely outside the environment, while I tested that I only had to replace the 7 functions for the commands on the chip, and all the other code was just compiled for the host and the other for the emulator. Probably that's what you have to do
Yes.
most of the time, that separate out your test cases, what is host only, what is emulator only, what can be mixed, and then navigate from that.
And the second kind of test is that you really have the right, like the normal kind of target software on your targets, and you have tests that test from the outside. But then you need a device that has, it's like public hardware interfaces. For example, if you have some network interface to your product, and maybe you can have acceptance tests. It's normally useful for acceptance tests or more system tests that you can exercise this interface or network. But if you, for example, if you have temperature sensors or whatever, or like you said, what did you have? You had a flash memory, or then it's hard to exercise it from the outside. You cannot say there's something in there. Yeah, there is, but you cannot trigger it from the outside. What's often good about these tests that they're kind of independent, and as you have seen, the framework I used is you could use that's the framework itself is Python, and not Python, Ruby, and you can compile some of the tests. You can compile in C++, where you really have your application, but you can also use Ruby, and then kind of if you just need a network interface, that's nice to do that. Something I haven't really looked into that much because it's maybe not that promising, I don't know, is to use emulators, where you really use the target software in your tests or compiled for your target, but you have an emulator. In Yocto, there is already one built. I didn't really try it out. And of course, then you still have kind of just the possibility to have test doubles for your hardware. But you could also extend the emulator with your hardware that you have available. We have here a colleague, he tried it once out, and he said it's doable, but it's so much effort that you really need to have a good case that it's worth the effort to do it.
I have not done it. I have colleagues who use QEMU a lot.
Yeah.
To do their testing.
Yeah. I think it
has worked out well for them.
Yeah. I think it really depends on if it's worth to get over the initial step to kind of get your hardware there.
Or if you're waiting for the hardware.
Yes, or if you're waiting for the hardware. I mean, those depends a bit what hardware you choose. if you have really something, if all your peripherals are proprietary, it takes a lot of time to get your peripherals into the emulator. If you use something more standard, then maybe there's already a lot available. And now not for your test. Yes, these were just the tests running on the host system. And now, so it fits better. Now, first here it's now an example, just the tests that were built during the TDD cycles. I just compiled them for my target. For the Raspberry Pi, that's no problem. So I can build them. And when it's built, it will hopefully deploy to the target. Yeah. Now you see the color has disappeared because it's over the network interface. But now this was just a test executing on the Raspberry Pi, but still using test doubles. So it was not really interacting with the hardware. Or wasn't it? Now the first test was just these test cases here. That's just what they also can execute on the host system. But there was a second test, kind of even test file, which did something else. If I'm now going to pull out my loopback cable and execute it again, you have seen that it fails now. What's not nice yet, because it's still work in progress, there is an implementation error which needs to, the test should give you feedback that the implementation needs some adaptations, that you don't need to kill your test with a... I could also blame it on the committee and say the standard future blocks when you try to destruct it. But I think it should more drive you in a way that your implementation is wrong and you need to clean it up. But at least you see if I take out the cable, now it already did, it was a unit test, it was special configured hardware, not the one I need for the product, but it did something with the hardware. And also for the acceptance tests, I have some tests that run against the... For that I also need a little bit of some special configuration, because what you often would do, you would try from the outside. For example, you have some GPIO expanders or whatever that your test can kind of trigger your hardware. What I now do is I'm just abusing the Raspberry Pi to itself being the external component that drives it. For that I need to put in a few cables. And now if I'm executing, you have seen it failed. And if I'm executing it again, it even made the sound. So the yellow cable was just there to basically press the button. So abused the Raspberry Pi for itself to push the button, which really triggered the whole chain. It triggered this one here to read out the button press and inform the other one, the Raspberry Pi, over a GPIO that the button was pressed. Oh. Yeah, that's more or less all, yeah. what I have to show you. So we've seen kind of this whole loop that I think should be applied also in embedded engineering. You could draw a lot of more arrows, because I think feedback should flow in all directions. So the picture would get a bit messy. We've talked a little bit about tool chains, or maybe a lot, about virtualizing the tool chains. Then these two difficulties that I really see are particular to embedded engineering is to find where should you put your test boundaries, because often you can do more is really appropriate. So you have kind of find the balance between what kind of work do I need to get like the best feedback, or that I don't do too much work, but what do I really need to do that I get the feedback that I really want. So to balance this, and it's also to do with where to execute your test. Yeah, that's all. Yeah, thank you. Some questions? Yes?
You built Linux-based operating systems for your hardware. Have you tried building Android-based operating systems for hardware?
No.
Because it's a nightmare.
That's you already have the answer. When a few years back, I thought now it's very nice that we have the Android on the ARM platform, because ARM gets really popular with embedded system when you can afford to have this, which is at the moment I think you really need to get in. You have really something very small that they say no, we're going with a 8 or 16-bit, or if not, then normally you have an ARM available. And then so this would be really nice, because you have it on embedded platforms and you already have the user interface there. But I've also heard what you told, that a lot of people say no, it's not suited for embedded system because it's not so easy as it seems.
Building a modified Android, it was not easy, and you need to download, basically it's an 80 gigabyte collection of 82 Git repositories and some scripts that manage them.
Yeah.
Including one Git storage file that's 23 gigabytes on its own. And yeah, managing that has turned out to be one of our issues.
Yes?
You're using almost entirely open source toolchain, which is brilliant, but if
Yes.
you find yourself in a team that are using Keel or IVR or one of the proprietary IDEs and toolchains, do you find there's friction there and you have to make those tools work the way the company wants them to?
That was kind of my first prototype to try out the idea of this virtualization. But often you have Windows-based toolchains. Like also at the customer I'm at the moment, they use IAR, and then you don't have a Linux version yet, I think, yes. We have a guy here from IAR, so we can ask him questions. And I'm not really sure yet if you can build up something with Vagrant, which works together with VirtualBox. But that's also something. Now I have a prototype, but to find out what do you really want to put where to get your toolchain virtualized. There's also some idea that instead of really on the developer machine to do that you try to get together. Often companies have systems for deploying software to all the users in the company with some centralized kind of installing or like a package system under Linux for Windows. And if that would be maybe a solution that you can make some packages that include everything, and also in a way that it doesn't interfere with something else, and then you can just, if you have a new member in your project, you can just say the IT is a member of that project and he gets automatically installed stuff. What I see is that there is some need to do something, because at the customer I'm at the moment, they really, a lot of the people have to maintain all the projects, and they really have a problem. It's often they try introduce a new tool or whatever, and then somebody says it doesn't work on my computer, and often it is because he has still some other tools that are interfering. Other questions? Yeah?
Traditional embedded world, especially predominantly C-based. Is there any experience of transition to C++ using or probably C++ features in that field?
Not that much yet. I think that if you have a bigger target like the Raspberry Pi or ARM-based, you can just use C++. And maybe even the newer, depending on what you really want to do, it's maybe even nice to have a newer version, because if you have a system where you want to avoid having a lot of, or not at all, dynamic memory allocations, templates are a great help to kind of have polymorphism at compile time. But for that, you would like to have newer features of C++ that you don't have to write really nasty template codes, or macros that kind of generate the template code, because you have variadic templates is something you then really maybe want to have. On the smaller one, it's still something I want to do. Now at the moment there is C code there. I would like to kind of write this code in C++ to compare. I mean, at least if you have a GCC, it's no problem to compile C++. Just then depends what features you're going to use from C++. Yes?
Just follow up really. I've done quite a lot of C++ programming on those tiny AVRs.
Yes.
C++ from the beginning.
I mean, the Arduino itself also compiles C++. I think I also did it before. Now I just did C because I wanted also to show that you can do the C part as well. Yeah. But I think if you want, especially if you want to go into having test doubles, then C++ may be nice to now it's really a fuss, and maybe you can also say this is kind of a code smell. I needed to add some more abstraction into, I mean, it makes my code more, there's more abstraction, so it's more modular. But maybe you say, if there is only one PVM I'm going to use, why do I need abstraction for that? It's just for the test. That's also something to be considered, which could be done maybe nicer and not lose the testability if you use C++ with templates. Other questions? I think we've, yeah. Okay then, thank you.